they are not proceeding that way. The atoms and the molecules, with their shape and their orientations, need to be arranged in a particular way, and really for practical purposes we only need to consider reactions in which one molecule falls apart, decomposes, rearranges, or reactions in which two molecules happen to hit each other. Yes, there are known reactions and wave constants for trimolecular reactions where three molecules need to hit each other, but it's rare. It's really something which barely ever you need to wait for. So as a consequence, it's really about reactions of one molecule or between two molecules, which we need to consider in all that we do chemistry. And those reactions determine the rates. And the rate is always what in the end determines the product, because at least theoretically all possible reactions are possible. But how fast they are determines what product we are going to get. And so everything in chemistry is about kinetics. It's always about which is a dominant reaction which reacts fast, so that all the other competing reactions are negligible or at least small. Okay. So if we have such complex reactions, then we can do various approximations, and we talked about them the last time. They're the steady state approximation and the rate determining step approximation. And they have many, many different names. The original is copied from the Levine textbook, but it is similar in all textbooks, of course, that there are no backward reactions indicated, because they are deemed to proceed at such a low rate that it's not really relevant. And that is an important takeaway message from what the book does over here. That if backward reactions are much slower than forward reactions, just don't take care about them in the beginning. You will get mathematical complexity without getting much of information about your system. Now, if you do your homework, and I'm not going to add to the homework much today, except saying this very thing. When you do your homework, please have a look at the second reaction, which is somewhat of a rate determining reaction in your homework. What about that backward step there? Is the backward step actually relevant if you were to neglect that backward step in your homework of the second of the middle reaction over there? Would things really change? So in looking at how reactions are, then it is always good to figure out what are the important things, and only use the important things in your calculations. So the only addition to your homework, which was assigned already on Friday, which is due on Wednesday, is figure out if you leave out backward reaction in the middle step, will something change? Okay. So if several reactions are faster, then take them into account. If reactions are slower, then they aren't. Also, if you look at the numbers for rate constants, that if you have numbers over here, take into account whether it's a first order or a second order reaction. Because typically, in most reactions, molarities are below, or molarities that you work in, are below 1. Very frequently they're much below 1. You're working at millimolar scale. If you work at millimolar scale, then just from the fact that you're millimolar, you have a 10 to the minus 3 in your calculation. So, for the rate. And then, if you have 2 millimolar reactants reacting with each other, you have 10 to the minus 3 times 10 to the minus 3, 10 to the minus 6 in there. So, the rate constants of second order reactions need to be generally much larger than the rate constant of first order reactions, so that the second order reaction can compete with the first order reaction. Which is just another way of saying it's unlikely for molecules to hit each other. So, but the bottom line is that if you look at the numbers in your rate constant, and if the second order reaction has not a much larger numerical value than the first order reaction, and you're working in the millimolar scale, which you usually do, then probably the second order reaction is much slower, is outcompeted by the first order reaction, and often just doesn't need to be taken into account. Couple of other things. If you have phase transitions, if in this reaction here, one of the reactants would evaporate, go into the gas phase, or precipitate, go into the solid phase, then clearly that reactant wouldn't be available anymore for the backward reaction. There is no concentration of something which precipitated, or at least the amount which was produced is in no way indicative of what the concentration in the solution phase of that phase. If you react silver with chloride and you have the silver chloride white precipitate, then the concentration of silver chloride in your solution is really, really tiny, because the silver chloride precipitates as solid silver chloride and then doesn't contribute anymore to the concentration. So if we were to look at the backward reaction, for that there is a very small concentration only. So, backward reaction in such cases, either disregard them or know the solubility constant. And the solubility constant might give you the amount of C in such a reaction. So the amount of C is constant in such a reaction step given by the solubility constant for C, how much you have, and not changing. So the deconcentration of C by T is not something which would change over T. It would always be determined by the solubility constant. So you have a different kind of weighting. If you use your Excel files, not a problem at all to just distinguish between the C in the solution and the C precipitate, and have two columns for it, and everything will work out nicely. Then also in your rate equation, it is often about how you run the reaction, and I think we mentioned that already earlier. If you add something dropwise to a reaction, then the concentration of that something in your reactor, in your container, in your beaker, or whatever it is, will change linearly as you add the concentration. So there is a dAdt if you put A in dropwise, which gives what is the concentration per drop and how many drops per second, and so on. So if you can always approximate or include the way you run the reaction in your rate equations. And if you do that in Excel, just have this other factor, this other term where you put things inside in your Excel file, and it will work. Okay, so now we spent about a week looking at how concentration affects reaction. Then the physical state, we spent about a few minutes now about that, and then much earlier we talked about gas phase reactions and how gas phase species zip through the room, and how unlikely or likely, depending on how you look at it, they are to hit other molecules and undergo reactions. We didn't talk much about the liquid phase, except that in electrochemistry we talked quite a bit about the liquid phase, and saw how motion of molecules are there. And we're going to talk a bit more about the liquid phase starting on either Wednesday or Friday when we look at transport. We talked about the heat temperature, because that's how we came from statistical mechanics. We looked at the Arrhenius equation and how the temperature affects the reactions. So catalysts are still what we have to look at for a moment. And catalysts are everywhere in chemistry. They are super important. Much of chemical research in the chemistry department, like here at UCR, is about making new catalysts, because these new catalysts can make reactions work better or allow new reactions to emerge. But all catalysts are different. Catalysts just don't work all the same way. So there's no way of saying the catalyst works, all catalysts work in this way, all catalysts have this specific effect on kinetics. But catalysts usually have to do with the barriers for reactions. Catalysts offer different reaction pathways, different sequences of steps in which reaction proceeds. Best way probably to think about a catalyst is as extra temperature, which you put in your reaction, which you don't need to provide a real temperature. Because as you remember, delta E over kT is what determines the rate of a reaction, and the catalyst provides you lower activation energy in reality, so the delta E becomes smaller, but you can think about it also as the T becomes larger and then the delta E divided by kT also becomes smaller. So think about a catalyst as added temperature, which is a real temperature to a reaction, and you will probably get a good idea, a good feeling of what the catalyst will affect. Very frequently, catalysts increase the rate both of the forward and the reverse reaction. It's not as clear in dry cut as it's written over here, because all catalysts work in different ways. And often catalysts offer not only one reaction step, but cut one reaction step into a myriad of subsequent consecutive reaction steps. So if we had a reaction as we're going to see example. Catalysis is important for two reasons, three maybe. It is important because it speeds up reactions. So you get more product. Or you get the product at lower real temperature, which has the benefit of you don't need so much temperature, energy, heat in order to drive the reaction. And also, sometimes that temperature or heat would be hard to handle both for the reaction system and the rest of your lab. And so you would, in order to have an appreciable yield of some reaction, you might need to increase the temperature of the reactants beyond the composition temperature for some non-desired reaction, and that wouldn't really work. But by using a catalyst, giving this extra heat, which is not temperature, by lowering the activation value, you can get the right results. And then also, a catalyst provides you with selectivity. Generally in chemistry, it's not as easy as in the textbook that only one reaction can proceed. Many different reactions can proceed at all times. And the catalyst will speed up one or a few of them, and not speed up many others of them. And so you're getting far more product of those reactions that the catalyst allows than of the other species. So if two molecules or a molecule were to react to two different stereoisomers, then if there is nothing chiral in the environment, you would get just the same amount of each of the stereoisomers. But if a catalyst is around, which speeds up the reaction to one of the stereoisomers, while not doing anything to the other stereoisomer, then you get way more of the one stereoisomer than the other. You don't get a reciprocation. And so, in effect, the catalyst controls what you got out of the reaction. And catalysts are frequently used for that very reason. So, in a quite general way, if I have a catalyst, this big sphere over here, and I have two reactants, the smaller ones over there, what a catalyst does is that a catalyst reacts with one of the reactant with a small barrier, activating that reactant, becoming activated itself. Then there is another smaller barrier where the second reactant becomes activated, also in the catalyst. And then on that catalyst, the two reactants interact with each other, the product is formed, there's another barrier for the products to release the catalyst, and finally you have your catalyst back and you have your product. And each one of these barriers is smaller than the total barrier in the absence of the catalyst. And that is why the catalyst is attacked. Note that the barrier here goes exponentially into the equation. The Arrhenius equation tells us that the rate constant is e to the power of minus delta E, that barrier over here, over kT. So it goes exponentially into determining the rate constant. So even if each one of these barriers here is 90% of the total barrier, we have 3 times 90% of the total barrier, that can still be faster than overcoming the whole barrier, which is 100%, just because of this exponential dependence of K on the barrier. So you only need to be a little bit lower in barrier than the original reaction, and the catalyst will be effective. So here we have that. That was not what I wanted. So in biology, catalysts are called enzymes. No good reason for that. Then they have different names. And reactants are called substrate. No good reason for that, but it's still a fact. So if we think about catalytic reaction in biology, it's enzymatic reactions, and the substrate gets modified. And very frequently, people think about them in Michaelis-Menten kinetics, as it's shown over here. Now, it's really just steady state approximation. But it has a completely different name here, it's Menten kinetics. And if you talk to the people working with enzymes and substrates, that's really what they think about. So they don't think about a rate-determined step approximation or something of that sort. They say, oh, it's Michaelis-Menten kinetics. So let's have a look at what is going on there. And that directly pertains to how those catalysts form. So if you think about a reaction of catalyst and reactant, written as enzyme and substrate, can react with each other to form a complex of the enzyme and the substrate. And that complex can dissociate again to become the enzyme and the substrate. So here we have an equilibrium. And then there's a second step of the reaction, where the enzyme modifies the substrate while they are in this enzyme-substrate complex, and the result will be that the enzyme releases a product molecule. The substrate is no more, it became a product, the enzyme is recovered. So if I want to figure out what is the rate of the reaction like this, or really at what rate am I going to make the product of that reaction, then the product of this reaction, the change of the concentration of the product in this reaction per unit time is of course given by the second slower reaction here that the enzyme substrate complex decomposes. And if you think about enzymes and substrates, people call this rate often V, like velocity, like the speed of the reaction, even though it is not really the speed, it's a rate. But that's what they do. So if I want to work with this one here, I need to figure out what is the concentration of this enzyme substrate complex. And that concentration in the rate determining step approximation is given as the equilibrium between the forward reaction of the enzyme with the substrate and the backward reaction of the enzyme substrate complex decomposing. And the rate of these two steps, rate of forward and rate of backward, is the same because those are much faster reactions. Those will be in equilibrium and then to get a near constant concentration of the enzyme substrate complex, which then could decompose. So the forward and the backward rate in this rapid equilibrium is the same. So the forward rate is given by K1 times E times S. Backward is K minus 1 times E times S. So now it's tempting to kind of cancel the ES out and just plug it in over here and say, oh, I have a solution. But that is not what people do. Because the concentration of the enzyme over here is not something which is really controlled in that reaction. What is controlled in that reaction is that a certain total concentration of enzyme is present. And the total concentration of enzyme is equal to the concentration of enzyme plus enzyme substrate complexes. Whatever total, initial, whatever you want to call it, concentration of enzyme you have is either in the form of free enzyme or is in the form of enzyme substrate complexes, which gives us a formula here that the concentration of the enzyme is the concentration of the enzyme initially minus the concentration of the enzyme bound in the enzyme substrate complex. Now, this one here is the one I plug in here. So I have K1 is times the concentration of the enzyme total I have here minus the concentration of the enzyme in the enzyme substrate complex times the concentration of the substrate equals K minus 1 times the concentration of the enzyme substrate complex. What I need over here is the concentration of the enzyme substrate complex. So, in order to get that, I need to kind of retrieve that. So I first multiply things out. K1 times the concentration of the enzyme, concentration of the substrate, minus K1 times the concentration of the enzyme substrate complex, times the concentration of the substrate equals K minus 1 times the concentration of the enzyme substrate complex. And then I need to bring this one here over to the other side. So I have K1 times enzyme substrate and then equals K minus 1 times enzyme substrate concentration plus K1 times enzyme substrate concentration. So I can then take this one here out and divide, and I get K1 times the enzyme concentration times the substrate concentration divided by K minus 1 plus K1 times the concentration of the substrate is the concentration of the enzyme substrate complex. Okay, so now I have a formula which I can put in over there. So the rate of that reaction is K2 times K1 times the total concentration of the enzyme times the concentration of the substrate divided by K minus 1 plus K1 times the concentration of the substrate. So that is the rate of my reaction. The people then still do a couple of modifications to this. They divide the K1 out of this one over here. So if you divide the K1 out of that, you get K2 times the initial concentration of the enzyme times the concentration of the substrate of K minus 1 over K1 plus the concentration of the substrate. Now you can identify something. Now things become interesting. If you think about this one over here, what is this? This is the total concentration of the enzyme, which is there. It is the concentration of the substrate, and typically the substrate concentration is much bigger than the concentration of the enzyme, so it's also probably fairly constant as a concentration. So, and this is the rate constant for the second step. This is the rate constant for the second step over here. So, if you wish, this one over here is the fastest possible rate you can have in your system. It is all the enzymes are assumed to be enzyme substrate. If all the enzymes were enzyme substrate complexes, then this one here would give you the rate of the reaction. So it's a maximum rate of the reaction times the concentration of the substrate. And the whole thing is divided by the backward over the forward reaction. So the whole thing is divided by something which governs the backward reaction over here. So that one is the dissociation constant of the enzyme substrate complex plus the concentration of the substrate. So if you want to look at enzymatic reactions, you will find that their rate, which is called V in that case, is given by the maximal possible rate you could have under an assumption that all enzyme which is present is bound to a substrate times concentration of the substrate divided by the dissociation constant for the enzyme substrate complex plus the concentration of the substrate and the curves which you're getting out of that. At low concentrations, they depend a lot on the substrate because more and more substrate is available to interact with the enzyme. If your substrate concentration is getting larger, then the rate will not so much depend anymore on the concentration of the substrate because the enzyme is really limiting the step and its ability to convert the reaction. Okay, any questions for this? Okay, fine. Now, another way of looking at catalysts, or another important part where catalysts are used, is in heterogeneous catalysis. When I put something in a different phase into a reaction in order to speed up that reaction. And very frequently, heterogeneous catalysis involves solid catalysts and a fluid, either a gas or liquid, of the reactants and the products. So a solid is a regular or not so regular arrangement of atoms which bound in more or less crystalline lattice. And people then think about how could that reaction proceed? Is it that two reactants over here are bound to the catalyst and then perform a reaction on the surface of the catalyst and desorb as a product? That was how I showed it in the slide a few slides earlier, where everything binds to the catalyst and then the catalyst releases a product. That is called Langmuir-Hinchelwood kind of process. And it is pretty much in all cases what happens. There are a couple of other ideas where, like, species from the gas fluid phase or gas phase comes on the reactant, which is held in place by the catalyst, and they then together desorb. But the green one here never reacted with the catalyst. There are known reactions which proceed that way, but they are rare. And finally, even more rare are reactions where one species comes onto the surface, retains its energy, uses the energy that is released when that species is bound to the substrate, becomes a hot atom because it still has the energy, it isn't thermalized yet, the energy for binding that, and then reacts with another species. There are reactions, people using ultra-fast lasers trying to find these kinds of reactions. There's lots of work going on in groups like Harry Thompson, CRISPR genes, and so on, and things like that, but yeah, not very practical. So, what does really binding to the surface mean? Binding to the surface means, like in this case, that we have hydrogen molecules and ethylene molecules. If I'm looking at the hydrogenation of ethylene to ethane, hydrogenation of ethylene to ethane, then I'll have those hydrogen molecules and ethylene molecules come on the surface. And on the surface, hydrogen will rather form a bond between a hydrogen atom and the surface than maintaining the H2 bond. Now there's of course again an equilibrium depending on how much hydrogen there is in the gas phase. There is a flux going on and off and on of the hydrogen, but there can be a population of hydrogen atoms where the atoms are individually bound to the particles. Now, those atoms don't need to be stable on the surface or stationary on the surface. Molecules and atoms absorbed to the surface in this fashion can move. The diffusion barrier for them is on the order of a quarter or so of the barrier for resorption. So the fusion of molecules on surfaces sets in much earlier than they completely leave the surface of resorption. So they can run around on the surface, those hydrogen atoms, rearrange themselves, lose each other and have no partner to bond anymore to desorb, or find each other and form an H2 molecule and desorb. Lots of dynamics on that surface can happen. And then also, if I'm interested in this particular reaction, the surface, like a surface of platinum atoms over here, then I might have an ethylene molecule right there. And the ethylene molecule interacts with the substrate by its outermost electrons. The outermost electrons of an ethylene molecule are clearly those ones in the pi bond. They are the farthest away from the carbon atoms, and so they are a kind of diffuse electron cloud, very similar to the kind of diffuse electron cloud that metal surfaces have in the first place, where electrons are delocalized in the metal and not close to one particular atom. So, delocalized electrons, that's what the metal atoms like. Delocalized electrons, that's a little bit like what we have in the pi bond. By having those diffuse large electron clouds, there will be an interaction between the materials. It is then a moot point whether you would say, oh, there is now a covalent bond between the platinum atom or whatever the substrate is over here and the carbon atom, and it's not really ethylene anymore, but it is the bond where we have 4 different bonds of this carbon atoms, 2 to these hydrogen atoms, 1 to that carbon, and 1 down here. It's somewhere in between those cases. But if that is the case, that means we now have a carbon atom here with diffuse electrons from itself and from the metal underneath, and a hydrogen atom that moves around and can come close to it. So at some point, that hydrogen atom diffusing around on that surface might bump into its own species, and then a hydrogen to carbon bond can form. At that point, this carbon atom has 4 clear bonds, 3 bonds to the hydrogens, 1 to the other. So now its second shell is full. It cannot and does not want to interact anymore with the metal underneath, and it will kind of tilt up and is ready to be far away from this electron density. So now it rearranges its position to lie over there. So now we have a new state. We have a barrier for the hydrogen to bump into it and then to undergo this reaction. The state which comes out of it is energetically more favorable because of this bond, and energetically less favorable because there's now lots of strain with these tilting molecules, in which of those 2 aspects is stronger depends on the particular molecule, the particular metal. But there might be another hydrogen atom, and it might also bump in this one over here now. And then we can have the desorption of ethane, which at that point has all its carbons saturated with hydrogen, not being able to bind anymore to the substrate. And we have, again, or still a population of hydrogen atoms on the substrate. So that is a heterogeneous catalytic process. Lots of research is done into using heterogeneous catalysts. Also lots of research is done into homogeneous and biological catalysts. But they each have advantages and disadvantages. In terms of heterogeneous catalysis, it has the advantage that separation of the catalyst and the reactant of the product is trivial. If the ethane and the hydrogen is in the gas phase and your metal surface is in the solid phase, you can just keep flowing the reactants over the metal solid, and you have no separation problem whatsoever. That is particularly appealing if you want to make a lot of it. Like you want to refine gasoline to make, refine crude oil to make gasoline. Lots of gasoline is being used, and if all the gasoline which is being used needed to go through the separation process where a homogeneous catalyst is removed, we couldn't afford it. It would be a very, very costly process. But using heterogeneous catalysts, separation of those tons and tons and tons of crude oil that are made into gasoline from the catalyst used to it is quick and easy. And so in such bulk and commodity processes, you have lots of heterogeneous catalysts. You also have less control in a way. The metal surface what you have underneath you, or the oxide surface which you have underneath you, there are only so many metals and so many oxides you can use. So if you use metal organic solution phase chemistry, like the drug, for instance, on the faculty here, then you have much more ways of modifying your metal with its organic ligands in order to have a very particular catalyst. And so you can make more precise reactions in that way. You can catalyze more specific one reaction over another one. But you have the separation problem afterwards because everything is in the solution phase. So it's more for specialty chemistry or pharmaceutical chemistry, where you have homogeneous catalysis, where you don't have bulk commodity style kind of catalysis you need to go on, but much smaller scale, where you have a higher value out of what you produce. But let's go back to what we are looking at over here. Let's go back to what we had in the beginning over here. Molecules are landing on the surface. And whoever drew out those pictures over here for a textbook, made sure that the atoms are all sitting in particular places on the surface. the ethylene molecule over here cannot sit anywhere or everywhere on the surface. It can only sit on the surface in a place where we have nice bonding between one carbon atom and an underlying metal atom, and the other carbon and underlying metal atom. Depending on the geometry of the surface, there are only a fixed number, maybe only one lattice of sites where it could be. It could be here, but it couldn't be sitting like here, for instance, because then the two carbons would try to attack the same metal atom, and that would be energetically different. So on every surface, there is a fixed number of adsorption sites, a countable and fixed number of adsorption sites with the same energy. Sounds trivial if I'm showing pictures like that, but it wasn't trivial when Mr. Langmuir found that out about 80 years ago. And so, after him, there is named the Langmuir model of adsorption. It was the same kind of Langmuir we had a few slides back, with the Langmuir-Hinshelwood kind of mechanism. Langmuir is the name. So he wondered, among many other things, how does the coverage of molecules on the surface depend on the pressure of the gases in the gas phase? And so, of course, what people then do is they think about kinetics. He thought about the process that molecules adsorb and molecules desorb, correct? Molecules can adsorb on the surface. There is a rate for the adsorption, and it's a D, it's not absorb, it's not a B, where absorb is getting into the volume of something, adsorb with a D is getting on top, on the surface of something, but not penetrating into its bulk. And then the rate of desorption. And those two need to be the same in order to have a stable condition. Now the rate of adsorption is, of course, the rate constant for the adsorption times the concentration of, or maybe I should just, times the pressure of the molecules on the gas in the gas phase times the number of empty sites on the surface. In order to have an adsorption event happen, we need to have molecules in the gas phase. How many molecules do we have in the gas phase? The pressure is linear to that, PV equals mNT, so P is proportional to N. So we also found earlier that the rate at which molecules impinge on the surface is proportional to the pressure. So the pressure is a good measure for that. And only if they come on an empty site on the surface, then they can absorb. On this surface you can absorb, on this surface CO molecules cannot absorb because all the sites are already blocked, occupied. The number of empty is 0 here. You would have no rate for the adsorption. Now the rate for the desorption is clearly given by a rate constant for the desorption. It doesn't depend on the pressure, because for the desorption the molecule just needs to go away. It couldn't care less what the pressure is. Times the number of filled site, because only, of course, if there's a filled site, the molecule can desorb from it. If the site was empty, then the molecule cannot desorb from it. There wasn't any. So let's divide this one here by the total number of sites. So what I'm getting out of that is the rate constant times the pressure times the number of empty sites divided by the total number. I'll leave that blank for a moment. And the K desorption is the number of filled sites divided by the total number of sites. The number of filled sites divided by the total number of sites, that is unitless, right? That's like a percentage. That's like which percentage of the sites are filled. and people use the word coverage for that. So theta, they approximate it, and they say theta is the coverage. The coverage is 1. If the number of filled sites is the same thing as a total number of sites, then we have a coverage of 1, all sites are filled. So the number of empty sites over here is then 1 minus the coverage. The number of empty sites is divided by the total number of sites is 1 minus the coverage. That's the empty sites, obviously. So at this point, we need to solve this equation for the coverage if we want to figure out what that is. So we have here K adsorption times the pressure minus K adsorption times the pressure times the coverage equals K desorption times the coverage. And then we can solve that for the coverage. We bring this one over here to the side and then divide everything out, which is in front of that. So K adsorption times the pressure equals K adsorption times the pressure plus K desorption, the whole thing times the coverage, and then the coverage becomes K adsorption times the pressure divided by K desorption plus K adsorption times the pressure. And in the last step, people say that's way too many K's over here. I'll take a new variable which typically is called B, and that is the equilibrium again between the constitutive adsorption and desorption. So it's the ratio of that. So I divide everything over here by K desorption. So I have K adsorption over K desorption, that is by B times the pressure. If I divide this by K desorption, then it becomes a 1, and then I have again my B times the B. So I get a Landry model of adsorption, which gives me that the coverage of a surface depends on the pressure and depends on this ratio between the two wave constants in this way. So if I'm going to higher and higher pressures, I have curves like this. If I have very high pressure, I'll get close to coverage of 1, coverage of larger 1, then 1 doesn't make sense because there can't be more sites than all sites being filled on the surface. And if depending on what this B is, I need higher and higher or not so high pressures in order to get to coverage like 1. Those lines over here have a name. Those lines are called isotherms. They're called isotherms because we know the Arrhenius equation. In the Arrhenius equation, each of the K's has dependence on the temperature. So, and they are different, those dependencies, for the adsorption, desorption process because they have different prefactors and different variables. And so if I change the temperature, what I really do is change the B, and then I get a new dependence of the coverage on the pressure. I get a new isotherm. Each line over here is at one temperature, different temperatures. Okay. And lastly, this is research which is ongoing. There is, I mentioned it earlier, lots of people in the department, including my group, is looking at heterogeneous catalysis. Other groups, for instance, are Francisco Zayera's group. And we are trying to find how reactions proceed. So research papers from my lab have pictures like that, but they look like barriers and look like how species are absorbed in small matter particles. And learn from that ways in order to make products in an efficient way. Okay. With that, thanks so much, and see you in the next one.